Everybody's so quiet here today before class. What happened? Is everybody okay?
No.
No? Well, let's go. Nothing is working.
Fine.
That just sounds like working in software to me. All right. Do we have questions about anything else before we get started talking about project two? Sounds great. Okay, they're too specific.
I did the contribution also. It's still Python. I don't know. It's terminating again and again. I'm not able to find what I'm doing.
Do you know what the error message is?
It is not providing any error message.
Is it a step failure?
No, it's just like there is nothing step or log coming. So nothing.
Okay. All right, we'll check it out after class. All right, project two. So this is going to be due on the Friday of Dead Week. You have 4 weeks to do it. And the idea of what we're going to do here is fairly simple. All of you remember connected components that we discussed while we were covering graphs early this semester? That's what you're going to do on your mutual links results. So you're going to take your mutual links results, and that forms an undirected graph, and we're going to do connected components on that graph. You look like you have a question.
Or connected components can be any degree away.
Yes. Can we're not limiting our iterations here because the graph in Wikipedia is quite wide, but it's not that wide. I have to run 32 iterations of connected components before it converges. And that's on kind of the simplest implementation. There are more complex implementations that will do it in fewer iterations. Um, but the simplest propagation algorithm converges in about 30. All right. What? All right. So your job is to take your original project one submission, and you all read this. Is this too small? More? Good. Okay. Your job is to take your original project one submission and treat that as an undirected graph and then do connected components on that graph. What I expect as output is the vertex of this graph, which is just the page ID of the page, combined with a component ID, which could be just a number. The component ID is arbitrary. It doesn't really matter what you use. I just used the smallest page ID within the component as the component ID, but you can do whatever you want. So you are welcome to use monotonically increasing ID or whatever else for your component ID. Every um, every page, part of the same connected component, should have the same component ID. Do we need a reminder of what connected components is? Wouldn't hurt? Okay, we'll go over that in a second. All right. So after you calculate those two things, what I want you to do is I want you to um, store the results of your connected components computation in S3. And I also want you to print out the top 10 largest components, their IDs, and their sizes, just in your log. So I can look at the. We've never done iterative algorithms in this class. And they function a little bit differently from what you did in Project One, in the sense that Spark gets scared when the DAG is too large. And so if you try to do 30 iterations all at once, it's going to break. And so what you have to do is you need to periodically checkpoint your iterations. What that means is, every 3 or 5 iterations or whatever you want to do, take your intermediate results, store them in S3, and then read them back. What this does is you'll notice that every time you do another iteration, another layer gets added to the Spark DAG. Because when you persist in iteration, it doesn't erase the data history from the rest of the DAG. It appends to it. So you don't want the data history to get too large. So what you can do to truncate the data history is write the iteration to S3 and then read it back. When you read it back from S3, Spark has no idea what was done to produce that data because it's an external data source. So that will truncate the data history. Does that make sense? So we're gonna go over the log file from a run that I did a few minutes ago of my code, and I'll show you what I kind of expect things to look like. Questions so far? All right. What?
For this project, the result for the correction of optimal project line summation for new members.
We'll get to that in a few minutes. All right. So, in order for this to work, you have to be able to read and write things to and from S3, but you can't always do it in your bucket because I don't have access to your bucket. This code is going to run in my account. So what I'm going to do for you is I'm going to provide an environment variable called CS535 S3 workspace. What this is going to do is it's going to provide a very similar purpose to the page pairs output, except that instead of giving the prefix for a single data frame that you're going to store there, it's going to be a common prefix for everything you're going to do. So all of the things that you store and all the things you're going to store, all of your iterations, all of your checkpoints, your output for the components, and your output for the mutual links all go in this prefix. Does that part make sense? Huh? There's one common prefix. You need to store a minimum of 2 things in there. You need to store your mutual link pairs, and you need to store the components that you've assigned to every page.
Mutual links pair that we did like for the project.
Yes, this is going to store exactly the same thing that you created in Project One. This is going to store your components, the components that you generated with your iterative connected components algorithm. And it's going to have these 2 columns. It's going to have the page ID and then component ID. And that's all. Everything else is optional, but I highly recommend you checkpoint in S3. I can show you the structure of my S3 prefix for an example. Question so far?
Is it like I owe one of the most time consuming things? Reading the disk, reading off the disk. So the fact that we are unnecessarily writing something to disk, which is what we need to write back in, seems like a super inefficient.
Somewhat, at least in terms of Spark, EMR FS or S3 FS is pretty fast, and it's not really the bottleneck. What's the bottleneck when it comes to reading and writing stuff to disk is memory swapping. So for example, when we do machine learning for our random forest model at Count, we use Spark to evaluate a bunch of transactions at once. the Spark machine learning model that we have is so big that it forces a bunch of disk swaps to and from memory whenever we do an inference. That absolutely kills the performance. And it's the perfect example because in Spark, when we don't have enough memory to hold the entire model in memory at once, doing 100 million transactions takes like 5 hours. When we can hold the entire model in memory at the same time, doing 100 million transactions takes 15 minutes. It's a big difference. And so reading and writing a prefix to and from S3 every few iterations is not really a concern. And so we do this all the time in, our identity building algorithm. Our identity building algorithm is an iterative graph algorithm, very similar to connected components, except it involves extra cuts. And it does exactly the same thing, is that every third iteration, it will write the intermediate results to S3 and then read them back, simply because Spark cannot handle a large DAG. It doesn't do well. It's actually kind of pathetic because it can only deal with like 4 iterations maximum before it just starts to get confused and start ooming all over the place, even if it has no business doing so. So if you can get it to work without checkpointing, I will be impressed. But I highly recommend you use checkpointing. That's the easiest way to solve this problem. And it will probably not be a noticeable time sink, at least in comparison to everything else you're doing. Any further questions?
Yeah, I have a question about the prefix.
The what?
For the prefix,
Sure.
so next we have the summary that we did in the project one, plus we asked for one more thing.
Yes.
What was that?
That is the actual component IDs.
The component.
Hey guys, if you're going to talk, keep it down.
Whatever we will print in the Wikipedia component here, that's a page ID and the component ID. That also we have to print in the mutual links, right?
You have to print the mutual links?
We have to we have to store them in the mutual link file in bucket.
I don't understand the question.
So in mutual link, we have to store the project one data
Yes.
and then we have to store the component ID.
Not in the same prefix. So those are two different tables. The mutual links table is the exact output from project one. It's just page A and page B.
Also, you want to print there, like you want mutual links to have like both project one output and project one. That's what.
No. Mutual links is going to have only project one output. Wikipedia components is the project two output. So how this is going to look in your S3 bucket is, so if I take, nope. Okay. So this is an example workspace. This is an example CS535 S3 workspace value. It's going to be something like this. This is going to be a common prefix for everything that you're going to do in your S3 bucket. And I'm going to submit this as an environment variable when I run your code. So if you want to checkpoint your iterations and submit your data set to a path that you can actually write to with my code, then use this prefix. So this is going to be the common prefix for everything. And what this prefix is going to look like is we can see the Wikipedia components output sometime today. There we go. Oh, yep. Okay. We can see the Wikipedia components prefix, and that's going to store just your two columns, your page ID and your component ID. You're going to have the mutual links prefix, which is just the project one data, and that's all. There's nothing else here. And your code is also going to be uploaded into here. It's not a big deal. And this is the checkpointed connected component iterations from when I ran my code.
If it's a global variable, can I just access the right it's needing in my Python code?
Yeah,
Okay.
it's os.environ. It's yeah, it's exactly the same concept as what we did in project one.
Explain this distribution part.
What? So I did go over how the connected components algorithm works briefly in an earlier lecture. We'll go over it again. Okay. Can't see my cursor. Okay, there we go. All right. So when you do this right to both of these prefixes, write it in Parquet format. Just makes it easier for me if everybody writes it into the same format, so write it in Parquet format. A small portion of your grade on this assignment is going to be reserved for corrections to project one. Now, most of you have had, some kind of correctness error, whether minor or not, in your project one submission. So you're going to want to fix those when you submit your project two. Because if you're basing your connected components output on project one and project one isn't correct yet, that's not going to produce good results. And I don't want those errors to cascade down. So I am going to make you correct them before you do anything else. Questions on that part? Okay. Now, some of you already did this for project one, which is great. And I need you to do it again for project two. So you need to create a small synthetic data set that tests both mutual links and connected components. So you are adding tests for project one, and that should help you, do the corrections you need to do for project one. So you need to add tests in this synthetic data set for project one and for project two. You can have multiple synthetic data sets if you want, but you need to have tests for both. You're only required to have a single synthetic data set. You can have more if you want. And because it's only a synthetic data set, you only really need to write one test. If you only write one test and you only have a single synthetic data set, you still need to test a bunch of different things in that same data set. If you want to do it with tiny data sets unit by unit, or just one data set where you combine a bunch of stuff together, that's fine. I don't care. I just created a single test because it was easier. Because I didn't want to make 15 files for every K.
So when I did a synthetic data set and I just tested it just in cells in my Jupyter,
Okay.
and you want me to actually create an automated test suite, like, do you want me to create like scripts that will run them? Oh,
You need to create an automated test suite that will run your tests when I tell it to run your tests. And that's really important because that means you need to write code that will take in both your synthetic data sets and the real data sets. So you need to use the same code in both your tests and when you're writing for real as an EMR step. Which means you'll need to introduce like some layer of abstraction into your code. Another thing is I want your synthetic data sets in JSON-L files. So one JSON object per line. And this is just so I can read it without having to do any funky things with deserializing a Parquet file just so I can read it. And I'll give you an example of what I expect your test suite to look like and what a project structure could look like for this in a few minutes. So I have my implementation of project 2 open somewhere, and I won't show you the code that you need to write, but we'll look through the scaffolding. Do I have anything to say?
When you do the checkpoints, how do you decide when to do that?
I just do it every third iteration.
Where we have stored your synthetic data set.
It's just in my repo. You need to submit your synthetic data set.
So you want us, okay, we have to provide the code for the synthetic data set that we extract.
So you need to provide the code that runs the EMR step. You need to provide the code that processes the data both in the test environment and in the EMR step. You also need to provide a test suite that puts your synthetic data through the code that you wrote and test the results. So you need your entry point that actually, governs and orchestrates how EMR is going to run the step. You need your code that's, your logic for creating your connected components. You also need your automated test suite that will take the synthetic data set that you created and pump it through your code. And then you have to assert that it gives you the results that you want. A test suite with no assertions isn't worth anything. So I don't want you manually checking the results of your tests. We good? Okay. And we'll see what this looks like in a few minutes. All right. So this project is worth 350 points. And the breakdown is as follows. 70 points out of those 350 are going to go to your code quality and your submission quality. Is your documentation good? Do I have to change anything before I run it? Stuff like that. When I use software in real life, software that just works is so valuable. I don't want to spend 15 hours parsing through complicated documentation to figure out how something will work. I love it when something just works. It's great. And if you can write something that just works, people you work with will love you. I'm not kidding. So when you write instructions to run something or test something or make changes to something, make it simple and keep it concise. This is where, designing interfaces plays a large hand in this. $40 points are for your corrections to mutual links. And the thing is that I'm going to be pretty picky with your correctness changes, in the sense that I expect you to make them. If you don't address every correctness point that I pointed out on your first grade, you're going to get points taken off here. So you need to address all the correctness docs I made. Is that clear? Good. All right. 100 points is the correctness of your connected components algorithm and dealing with that correctly. No surprises there. 70 points is for the quality of your test suite and automation and automating the test suite. So the quality of the test suite basically means that the assertions are actually meaningful and that you're testing an appropriate range of cases. So I don't want you to just test one thing, the simplest thing. Don't just test the happy path, right? You got to test some of the edge cases too. And you have to test both mutual links and connected components. So make sure all of that's in there. Make sure it's automated as well. Make sure I can just run a command and have the test run and hopefully pass.
For that, for the synthetic part, we're not doing anything necessary. We're just doing.
It'll just be local. Yeah. So my synthetic data set is stored locally, and when I'm running the test, it only reads from local files. And during my testing, it also checkpoints even when running the synthetic data just because. So the workspace for checkpointing the connected components iterations also loop when I'm running the tests. All right, and lastly, I was really happy with everybody's code performance in Project One. So I know Project One took 75 minutes, and I'm not saying that the connected components code should take 15 minutes to run. And so the performance constraints are a little bit tighter here. And so your code needs to run in 90 minutes. But I'm giving you double the resources this time around. So I'm going to run it on 2 R6 GDs, not 1.
And that's for running and generating neutral links, or is that running?
All of it, all of it. All of it, both combined.
Would you recommend that we develop on that as well so that we like fail faster?
Yeah.
Okay.
You can develop on something even bigger if you want. The other thing is that Spark Connect doesn't handle large numbers of iterations very well. And the session tends to just not survive that. So when you're testing like all 30 plus iterations, you can have a more efficient implementation if you want. But when you're testing all of your iterations, you probably just want to do it as an EMR step. EMR is a lot more stable than Spark Connect is. And so there's a much lower chance that it'll just randomly die. So for the first few iterations, you can test that in Jupyter Notebook, but when you're ready to go all the way through, I would recommend doing it as an EMR step. Does everybody have like submitting the EMR step down? Do we all know how to do that? Okay.
I'm still facing it.
You're still fake. Yeah, we'll figure that out. I know you've had special problems. What with your account and all of that. So we'll figure it out.
I have a question about the sort reflection. You mentioned 1 to 2 paragraph on board project. One in project you're going with just to submit that.
In your README. In your README. All right. And the submission process is a similar deal to what we did last time. Create a private Git repository. It needs to be private. Invite me as a collaborator. If I see commits past the due date, I'll roll it back, yada, yada, yada. We all know that. All right. I'm going to emphasize once again, you may not submit a Jupyter notebook. I know that nobody submitted a Jupyter notebook last time, which is great. The problem is there were a few individuals that simply exported the Jupyter notebook as a Python script and submitted it without running it. Do not do that because there is a very good chance that the script will break and won't run. So make sure you actually run the script that the export generates before you submit your code, please. Are we clear with that? Okay. Now, last time, if you were not able to get your code running as an EMR step, I didn't take points off because not very many people managed to get it working. If you did manage to get it working, I give you extra credit. However, it is a hard requirement in the submission. I will, because I had to make, small changes here and there to almost everyone's code in order to get it to run on EMR. I will not do that this time because we're submitting it close to the end of the semester and I don't have time to do that. So your code has to run as an EMR step. I have to be able to just press go. And like I said earlier, we're going to use 2 R6GD 2XL instances in the core group this time instead of just 1. So you have a bit more resources to work with here. You won't need them. Like I got this to work just fine on a single R6GD instance. And Obviously it took twice as long because we have half the resources, but you know, we're not really constrained by that. It's just for convenience's sake. All right. Lastly, include a README in your project. And like last time, you need to tell me what the entry point file is, and you need to provide a script to generate the zip file that we're going to submit with the EMR step. Now, I know a lot of you had a single Python file as your submission last time, which is fine, but since we have to use since we have to write tests now and everything, you're probably going to have code in multiple files. And so at that point, it's going to become necessary to create a zip file with the rest of your dependencies in addition to the entry point file. We good? Good. Give me instructions on how to run your automated test suite. So give me a command that I can run, and it should just run your test suite. Next, in your README, I want you to describe your synthetic data set, describe the cases that you're testing in your synthetic data set, and describe whether this case pertains more to mutual links or to connected components. Because what I found when I was writing my test data set is that I had one set of rows that was specifically meant to test mutual links and another set of rows that was specifically meant to test connected components. But I had to place them all in the same files because before we run connected components, we have to run mutual links. But I found that I had, two distinct sets of cases going on. So there's that. And lastly, give me a reflection, 1-2 paragraphs on both project 1 and project 2. I should have asked for it on project 1 and I didn't, so I'm going to have you do it this time for project 1 as well. And I want you to tell me, in your development process, what did you learn here? And where were your difficulties? And this is especially because if I find common pain points, I'm going to want to address them in future semesters. So I want you to tell me in what places you had the most difficulty with this assignment, and just tell me something interesting you found about Wikipedia's dataset. Like, it's a complicated dataset, there's plenty of garbage in it, and it's real. There's something interesting in here. Even if it's not that surprising. So it doesn't have to be a surprising result, it just has to be interesting. And lastly, I think I told you this last time, there are 2 due dates for this assignment. The first due date is at the end of dead week. And that's going to be your first submission. I'm going to run your code. I'm going to grade it in, a day or 2. I'm going to give you all back the grades. And after I give you back the grades, you will have the opportunity to correct them and submit it again a week later. Not exactly a week later, on the Thursday the following week. And this is so I have time to grade it on Friday because I'm flying on Saturday. And just because we have 2 due dates doesn't mean you can skip the first one. You have to submit by the first due date.
Will you get extra points for
No, that's just part of the assignment.
that?
All right. That's pretty much everything, at least for the spec. And we'll go through the nuts and bolts of the test suite pretty soon. Are there any questions on the spec? Okay, now let's go through what I expect your test suite and or project structure to look like. Obviously, it doesn't have to be the same as mine, but something like it is good. Okay, you can't see this. Yep. Okay. So what we have here, let's start with the entry point file. This is just the orchestration for the entire project. What we do first is we start the Smart Connect session, or not the Smart Connect session. this is running on an EMR step, so there's no Spark Connect session. We start the Spark session and we start, we create this object, and I'll tell you about this later. This is a technique called dependency injection. And what this does is this abstracts the handling of writing to and from the workspace. Because when we're running it on EMR, the workspace needs to be in S3. When we're running the test locally, the workspace also needs to be local. And the handling of it, the code is also slightly different depending on whether we're running an EMR or we're running locally. So I have two different implementations for this interface. It's called DFIO, which is just data frame IO. Data frame read and write. That's the only thing that's in here. Okay. Now, how this is structured is because we have two possible different sources of the page table, the link target table, the redirect table, and the page links table. One possible source is the real data in S3. The other possible source is our synthetic data set. So I pass in all of the data frames that we would need in order to create the mutual links. That's what this is for. Does that part make sense? Yeah?
You need to have a synthetic data set.
Yeah.
The synthetic data set and the data set that you have provided. These two are two different data sets, but the both should give the output through one code only.
Yes.
Right. So when we are pulling the data set through our code, how we can make the data set with some data?
So after you read it into a data frame, it should look exactly the same, regardless of where you read it from.
Upload the data set in JSON file, right?
You need to upload your synthetic data set in the JSON.
Yeah.
Yes.
We have to get that data set from there on.
From where?
JSON file. When we are running the code, we need to get the data set from there.
When you run the code as a test, when you're running your tests, it needs to read from your synthetic data set. When you run it as an EMR step, it needs to read from S3.
Okay. 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 So,
No, it's all right. You can ask now. Okay, yeah. Will this will make sense once you see the different pieces of it. This is just one piece.
Where does your create things and your parquet, where's all that spot?
It's a mutual links file.
Oh, you imported it up. Okay, so in your entry point, did you import the mutual links? Is that what you did? From mutual links, imported those things.
Yes.
Oh, never mind.
Okay. So you need to pass in, your data frames for these four source tables. The actual source of those tables is going to vary depending on whether you're running your tests or you're running it for real in EMR. And so the only thing we're doing right now is we're using, this abstraction to write mutual links to our workspace. So that's what this does. And over here, this reads it back again. And this is for the same reason that I am, periodically checkpointing iterations, is because we don't want the DAG to get too large. The DAG for mutual links is already quite large. You've all seen it. So I'm truncating that DAG as well here. That's what this is for. Make sense? Okay. All right. So what we need to do now is we need to start the connected components algorithm. And the connected components algorithm takes 3 arguments. It takes our data frame reader writer object. It takes our edge list of the edges in our undirected graph, which is just mutual links. And it also takes a Spark session. And right here, this is just a renaming from page A and page B to source and destination, because I wanted to make this connected components algorithm just a little bit more generic, because there's no reason it has to only work on the Wikipedia graph. So it can work on anything that has a source and a destination structure for a graph. So that's why we're renaming it here. So after we get the connected components, we write it back out. Yeah. So the original Wikipedia graph is directed because links go in a specific direction. Mutual links is undirected because it doesn't matter which way you express them, it means the same thing. Right? If A has a mutual link with B, then B also has a mutual link with A. It's kind of like Facebook versus Twitter. When you're friends with somebody on Facebook, that relationship always goes two ways. So the Facebook graph is undirected. On Twitter, you can follow somebody without having them follow you back. So it's Twitter is directed. Does that part make sense? Connected components is a lot more complicated in a directed graph. So we're going to work with an undirected graph. Because there are actually two different types of connected components in a directed graph, not just one. There's weakly connected components and strongly connected components, but this isn't a network class, so we're not going to go over it. And also because I would need a refresher on how it works. I haven't dealt with directed graphs, or at least those algorithms, for a long time. All right. Questions on this structure so far?
Mention of a company ID.
Yep.
How do we get that?
You have to generate it. It's arbitrary.
But what's the connection? Like, how to get that company ID? What is what connected?
Huh?
How to get that company ID? What is this your component ID?
It's just a way to express that different pages are part of the same connected component. That's all it is. It's a way to express that.
Okay, that how all the four data set is connected.
All the four data set?
Link target, redirect, and page number.
What about it?
When you talk about the connected component IDs,
Uh-huh.
so how you are relating that thing from the code of those data sets?
It doesn't have to be related at all. It's a completely arbitrary identifier. It only exists to communicate that two different pages are part of the same component.
Okay,
You can make it whatever you want. You can randomly generate it and then propagate it out. What I chose to do, because I'm lazy, is I took the smallest page ID within the connected component and I made that the component ID. That's it.
smallest page ID, and you made that
As the component ID. And I like doing that because it's less work because the identifier is already there and it's also deterministic, which monotonically increasing ID is not. So you can just use the smallest component. You can just use the smallest page ID in the component.
component ID and size of the largest component.
Yes.
So when you talk about the size of the largest component, what is the size?
The number of pages that belong to that component.
Okay.
And I'll show you what the output is expected to look like.
Okay, please.
Yeah, we'll get there. We got 20 minutes left, 25. We'll get there. We have plenty of time. Okay. So what this does is this takes this shows the size of each connected component. Like that part's easy. Okay. So this is kind of how mutual links is structured. So for this DFIO class, this abstraction where you read and write to and from the workspace, it only has two methods. It has reading from a path within the workspace, and it has writing to a path within the workspace. And so we just use the workspace environment variable, and we base our reading and write paths based off of that. Cool. Okay. And so this just contains the same code as last time. And we input our, four source tables into there, and this function returns a mutual links data frame, which we then, turn into a graph and pass it into components. That part makes sense? Cool. And connected components needs this DFIO object because connected components is going to periodically checkpoint and write to the workspace and then read from it again. All right, let's look at the tests. Okay, so here's how these tests look. And you'll notice that we have another class called DataFrame.io synthetic. And the interface is exactly the same as the other DataFrame.io, except its implementation looks a little bit different. Its paths are based off of just the current working directory where you're running the tests. And it's reading in JSON instead of Parquet. That's the only real difference. Questions on that? Okay. So what? Yeah. So I only have really one data set, and so one test. And in this example, we have a list of our expected links. And that list of expected links is to test the mutual links output. So this is just a list of pairs. And keep in mind that this is a frozen set. And so it's really easy to compare two different frozen sets using Python assert equals. It's really nice because if you create a frozen set of tuples from your mutual links and then compare it to what you expect, assert equal will actually tell you the difference between the expected set and the actual set. It'll say, these elements were in this set, but it wasn't in the expected set, or these elements were in the expected set, but they weren't in the actual set. So it's really nice. And a frozen set, yeah, what? What do you mean?
Are you from, where are those expected links values?
They're in here. It's collapsed.
And you are just, those are literals?
Yeah, they're tuple literals.
Oh.
Does anybody have questions on what a frozen set is? So a frozen set is exactly the same as a normal Python set, except it's immutable, which basically means you can use a frozen set as a hash key. I think we covered this briefly in one of our really early lectures. You can't use a normal set as a hash key because a normal set is mutable. But a frozen set is immutable, so you can use it as a hash key. So you can actually make a frozen set of frozen sets, which is what the expected components variable is. It's a frozen set of frozen sets, which makes sense, right? Because within a connected component, there's no real meaningful order. And among the connected components, there's also no meaningful order. So when we, collect these, connected components and put them into frozen sets to compare, this makes it really easy to compare the two. So you can see how this works. We call the exact same mutual links code that we do in the entry point file, except instead of reading Parquet, we're reading JSON. And that produces a data frame that looks exactly the same as the original real files that are stored in S3. So we create this new data frame IO synthetic object that will read and write from the local workspace in exactly the same way that the original DFIO class from the EMR step will read and write to and from the S3 workspace. The interface looks exactly the same, so Python can just call the object. This is called polymorphism or dependency injection. We have different implementations for the same interface that depending on your environment, we want to do different things. We do this all the time at Count Engineering and everywhere in industry. This is everywhere. This is so common. Questions about how this works? Sweet. Okay. So now we can just assert, create a frozen set of tuples, and every tuple is just one of our mutual links. And we do exactly the same thing when we run connected components is we will take the result for connected components and we will form a list for every connected component. And so what we wind up with is this members column is an array containing every page in the same connected component. So that way, when we collect it, we can turn every one of these arrays into a frozen set, and all of those frozen sets can be part of the set of connected components. So this expected components is a frozen set of frozen sets. And it's nice. We can use frozen sets as hash keys. It's just really easy to express that way. Questions on this structure?
We are recording this lecture on that side.
Yeah, I better be recording this lecture. Everybody in this room is going to be really sad if I'm not. Yeah, okay, we're recording. We're good. We're also screen sharing. Yes. We're also recording, so that's good. And we're screen sharing and yes. Because I know that last time I recorded the entire session without sharing my screen once, so it's just a black blank. I'm sorry about that. I've done that like 3 times this semester.
Those, the like page link target, those are all the name of the JSON files you have.
Yeah. So if you look at the file structure over here, there's test data, and then link target.jsonl, page.jsonl, page links.jsonl, redirect.jsonl. And
You have created code in the
yeah, one for each source. So I'll show you one of them. This is what it looks like.
The L is just that it's an object per line.
Yes.
L means-
It's so that VS Code doesn't whine at me about having a syntax error in my JSON file.
Oh, is that, wait, is it literally just that's the only difference between that and a regular JSON file? Oh,
JSON-L stands for JSON lines.
I was like getting ready to learn a whole new format.
No. It's not different. It's not that deep.
Gotcha.
So just submit a few JSON line files for your test data.
Okay.
It's up to us, like 8 lines or 10 lines. It's up to us, right?
You can have as many or as few test cases as you want. Just make sure they adequately cover what you're trying to do.
How is this test script flipping between running, like it looks to me like it's set up to run this locally. How is it then running on for my S3 data? I'm actually.
Well, that's part of the abstraction layer, right? Because mutual links, the create links function works on both synthetic data and real data. And so in the entry point file, we pass in the real data as a data frame. And because this is a data frame, it looks the same as the synthetic data would look as a data frame. So this code, this function has no idea that we're reading and writing from Parquet. It has no idea that we're running locally or if we're running an EMR with S3 data or whatever. It has no idea about any of that stuff. It just deals with the data and the data structure.
Wait, test script does. The test script is reading your synthetic data.
Yes, but it's calling the same function. It's calling the create links function with different data. So it's passing in the JSON data in the tests, but in the EMR step, it's passing in the S3 data.
You're not set up to run your test script with your EMR data though.
I mean, there's no reason I would want to do that because the test script runs locally. Like the test script will run on this machine.
Right, but if you're designing tests, wouldn't you want them to then run on your cluster for your whole data?
I mean, we could. That's the way we do it in our identity pipeline account, but I'm mainly just testing the logic.
I thought you wanted testing build run on either.
Yeah, you don't need to write a test suite that runs an EMR. So as long as your EMR step and your synthetic test is roughly similar, then I'm okay with that. Yeah.
Like test suite, it has all of the namespaces as zero. Could you just stick to the namespace of zero? Because I like for the last project, I started trying to test namespaces and I'm confused myself.
Okay. Yeah, you can leave all the namespaces as zero. You can change your original project one implementation to only deal with articles if you want. All right. Want to run the tests? Let's run the tests and let's see what this looks like. Okay. So it would be that's not how you spell Python. Jeez. Nope. There we go. It's starting the local Spark session. Computing. This takes a couple minutes. Oh, there we go. Okay, now it's starting connected components, iteration 0. Right, iteration 1. And you'll notice that it's keeping track of the number of vertices that have changed in every iteration. That's what that log means. And that was just for my benefit. Because I wouldn't be able to create an automated test suite. This test suite needs to be automated.
It's not really running locally though, is it?
It is running locally. It's running a local Spark session on this machine.
Does it terminate it?
Mm-hmm. All right, changed vertices equals 0. That means we exit out, and now we're done. Yay. Okay, so I, engineered my data set so that it would require 4 iterations and it would require a checkpoint. So it checkpointed, and we can see in the test workspace that it has a checkpointed iter3 directory with some files in there. Make sense? Okay.
File runs we do test.py for us, then only we have to move for the EMR thing, right?
What?
This, you have tested this for JSON file, right?
Yeah.
So after this work, then we have to move for the
Then you have to run it in S3 for
EMR,
real.
yeah.
Then you have to run it in S3 for real. This takes 20 minutes to run, so we're not going to do it live. Also, we don't have time. But there is something. I do have something that ran right before this class. right here.
So you will provide these things, no? Start, the entry point and all those stuff.
No, entry point is your job.
You're not going to provide these notes.
I'm not gonna write your code for you. I gave you a start emr.py. You can still use that.
You have this is in process side, assignment first from me.
It's not different. It just has more code. So you might need to upload the zip file in addition to an entry point, but that's it. Okay, this is what the example output looks like from my step. Okay, so we start this work session, we create the mutual links, we start the connected components algorithm, and in order to do that, we have to create, at least my algorithm uses bidirectional edges, so we clone them. And we create a list of vertices, and you'll notice after every iteration has exactly the same number of rows, right? Because we're continuously updating the current component for every vertex. We're not gaining or losing any vertices. So this is expected behavior. And so you'll notice that every iteration, there's a number of vertices in this graph that change their component ID. And this is the number that tells us how many vertices are changing their component ID. So we have a little over 6 million vertices in our data set. And on the first iteration, we change 5.8 million. On the second iteration, we change 5.85 million. On the third iteration, we change 5.8 million again. On the fourth iteration, we change 4.8 million. On iteration 5, we change 1.8 million. This is going down fast. You should expect this exponential decrease. This exponential decrease with a long tail, because the last fringes of the graph are going to take a while to fill out. So right over here, like this has 1.8 million. This has only, 380,000. And after that, we have 120,000. After that, we have 18,000, and then 1,600, and then 500, 200, and then we have this is an iteration 10, and then we have a long tail all the way down where we go by a little bit on every iteration. Yay. Yep. We're only changing 9 vertices in this iteration and 6 vertices in this iteration. Isn't life fun? And then we change only 1 vertex in this iteration, and then on the 32nd iteration, we're finally done. Okay. And so now when we want to get the component statistics, we have 36,000 components. We have 36,000 connected components. And we can also look at the top 10, 20-ish connected components and their sizes. This is the component ID, which is 12. And this has almost 6 million almost 6 million pages in a single connected component. This is expected. Lots of real-world networks look exactly like this. Is you have one giant connected component and then everything else is on the fringe.
So the page ID 12 is a part of that. And now
There's nothing special about page ID 12. It just happens to be the lowest page ID in the connected component. It's not a statement of its centrality or anything.
This is the final output that you're looking for, right?
Well, you have to output it into S3 as well, but yes.
Yeah.
Does this project make sense? Do we have any questions? Doesn't this sound like a fun time? No.
If you asked.
I mean, I think the algorithm is more complicated than the first project, but the data is a lot simpler because you don't need to deal with any crap now. Because theoretically, after project one, you've curated the data and it's no longer garbage. So this is your data that you're dealing with right now for connected components. So if it's garbage, it's your fault.
What does that tell us about having almost all of our grammar is one graph with just little things around the edges?
It tells us it's a normal network.
And
If
how useful then is putting it into these networks? Like,
so, connected components is mainly an exercise. It does have relevant use cases. So the best example I can think of for connected components use cases are Count's persona system. Count's persona system is a real-time database that runs connected components. That's called dynamic connectivity. Is every time you add a transaction to the graph, it updates the connected components in real time and then returns it. And
does that limit the number of connections? Or is it follows your lines all from the connections?
Depends on what version of persona you're talking about. The version I wrote does do that. The version in production does not. But that's because the version in production has a bunch of other requirements that I don't.
But it can't look like this, or it would not be helpful.
No. So what persona does is to limit the size of a connected component, it will age out edges after 2 weeks. Because you're right, it would just look like one giant connected component. Because that's pretty much every real world network is one giant connected component. So this isn't a surprising result to me at all. But I thought it was cool to show you. And the reason connected components is a useful exercise is because it's probably the simplest graph algorithm. And a lot of other graph algorithms look really similar to connected components. The identity building algorithm that we have at Count is very similar to the connected components algorithm I use here, extremely similar, but with a few small tweaks. But even though the algorithm is similar, the effect it has on building the identities and um, delineating different subgraphs is so different from connected components. So even though the algorithmic differences are small, the actual effects it has on the result data are huge. So knowing how to do this is super helpful. It's kind of the basics, the basis for every other graph algorithm you're going to run.
So if you had this data and you were trying to, I don't know, I assume you'd start with the use case, but if you had this data and you was in a graph, and you were to look at this, you'd be like, okay, yeah, that's normal. It's mostly all connected. What could this type of clustering help you with? Like, what would you do to actually find out something useful about your data?
So that's the entire idea behind community detection is how do you find a subset of nodes in a graph that is more connected to the other members of that subset than it is to everything else? And like I said, connected components doesn't do that. But since a lot of different algorithms are so similar to connected components, this is the most general way to teach you how to do this. I don't know. It's kind of like when people say that going to school wasn't useful because they don't use Java in their job. Because it's like, well, because you learned Java, you know what a string is, and that's transferable to everything. And so is this. This is transferable to every other big data graph algorithm that you would ever run. Any questions before we leave?
This is the result for the input from the right?
Huh?
We have to print the component and the size.
Yeah. Print the top 10, top 20 component sizes and their IDs.
Synthetic data as well. We should be printing.
You don't need to.
Can you show the output for the synthetic data set that you just did?
So the output for the synthetic data set is really similar to this because it runs the same code.
Not received in table.
So it'll create the bidirectional edge list. It will create the list of vertices. It will then it'll start running connecting components and it'll go through the iterations. And you'll notice between iteration 2 and iteration 3, we do a checkpoint. That's all.
So this is just to basically check if it's working or not.
Yes. Yes.
Okay.
Anything else? All right. See you later.